Hello everyone. Today we will be discussing the basic ideas of statistical mechanics. I will be giving a brief introduction on statistical mechanics. Statistical mechanics deals with the macroscopic properties of a system like pressure, energy, entropy, etc. But all these macroscopic properties will be depending upon the microscopic properties of the constituent particles. These microscopic properties are responsible for the macroscopic properties like pressure, energy, entropy, etc. Now, in statistical mechanics, whatever equations we derive, on the right hand side there will be a temperature. Basically, all the equations that we derive in statistical mechanics will contain temperature on the right hand side. For example, if we are finding out the susceptibility of a paramagnetic material, susceptibility is given by Curie's law, which is chi is equal to C by T. You have T on the right hand side. It is in the denominator, but C is there on the right hand side. Another example that you can have is an ideal gas. In the case of an ideal gas, the basic equation of states are PV is equal to NKT or P is equal to NKT by V. E is equal to 3 by 2 NKT. On those two equations, you will be able to see T is on the right hand side. Therefore, statistical mechanics aims to find temperature dependent properties of a system. Now, a system means a collection of molecules or atoms, it can be electrons, it can be photons, etc. If you take some atoms or molecules inside a chamber, you will be able to see that atoms and molecules are vibrating, they collide with each other, they collide with the walls of the container. Anyhow, they are moving inside this cavity. And whatever properties that we measure will be the effect of the collision or effect of the collision with each other or effect of the collision with the walls of the container. And they give rise to, for example, pressure. Pressure exerted by atoms inside a cavity is actually an average property, and that average property happens after a particular interval of time. Therefore, whatever average property that you find in statistical mechanics is actually the time average properties. Time average, it will be always a time averaged quantity. For example, if I want to find out what is the velocity of the particle, the total velocity of the particle, what I have to take is, velocity means, for example, for a particular instant, if I am interested in finding out what is the effective velocity of the particles, each particle, if you have n particles inside the system, each particle will be having independent velocities, and those velocity will be continuously changing because they collide with one molecule. If you take one particle, it collide with another atom and then it collide with the walls of the container, it changes its direction, the velocity every instant it will be changing. Therefore, for a single molecule itself, if I want to find out, for example, if I want to find out the velocity for about 10 seconds, I have to find out all the velocities from 0 to 10 seconds continuously, and then I have to take the, if I want the effective or the average velocity, I have to take the time average, and that time average is given by average V is equal to 1 by T. I represent that time because later I will be representing that T by temperature also. Therefore, I will be representing by a suffix T there, 0 to T V of T dt. Why I am finding out this velocity? Basically, I am interested in finding out temperature or pressure or energy, etc. Therefore, by equipartition theorem, I have half mv square is equal to 3 by 2 nk T, where T is the temperature. Therefore, if I want temperature, I can cancel those two, and then rearranging, I will be able to get T temperature, or temperature will be equal to m by 3 nk sum over all these velocity, average velocity square. And if I want to find out these velocities of different molecules, I am summing from I equal to 1 to n. That 1 to n indicates the number, the different particles. Therefore, if I want the temperature in statistical mechanics, I have to take the time average of the, if I want temperature, I have to take the time average of the square of the velocities for all the n particles, even for a time t equal to some 10 seconds. This is a laborious process, almost impossible, because in a small container you will be having more than 10 raised to 23 particles and summing over all the velocities and then finding the time average, it is really impossible. Therefore, whatever average property we will have to find in statistical mechanics is always the time average, and finding the time average is actually not possible. Affirmatively you can say it is not possible in statistical mechanics. This was the scene that was in 1900 when Boltzmann was doing statistical mechanics problems, and then he put forward a theory or a theorem which is known as the ergodic hypothesis. Ergodic hypothesis. According to Boltzmann, this time evolution for a long time, you can replace that by, or actually the system will be passing through all possible states. Boltzmann said the system will be passing through all possible states that is available during that time, and that idea was changed by Gibbs in 1902. He put forward a theorem which is called as the Ergodic Theorem. Accordingly, all this time average you will be able to convert or change into ensemble average. You will have to change into ensemble average. Actually, that ensemble average replaces the time average, and according to Gibbs, if I want to measure, for example, if I want to measure the average energy, and if you have a large number of systems represented by I equal to 1, 2, 3, 4, etc., average energy I will be able to find out by using the equation sum over I is equal to 1 to n or some 1 to infinity or something like number of states. I represents the number of states. Therefore, if n1 is the number of particles in the first state, n2 is the number of particles in the second state, each having energy E1, E2, etc., then the average will be given by average E will be equal to sum over I is equal to 1 to n, n1 E1 plus n2 E2 plus n3 E3 etc. whole divided by n, That is, in general I will be able to write any average as average of x is equal to 1 by n sum over ni xi. I am replacing energy by another variable, that is x. That n is outside the summation. What Gibbs did is he took the summation inside the summation, took the n inside the summation. Therefore, the equation now becomes sum over I is equal to 1 to n ni by n ei or xi. Xi is the instantaneous value of the property that you have to find, and average x, the bracketed x is the average value of that property. What is ni by n? For example, if I have a dice, if I throw a dice, I will be able to get, if I want to find what is the probability of getting 2 out of the 6 sides is 1 by 6. If I want to get 6, it will be 1 by, the probability of getting that particular number will be always equal to 1 divided by total number, that is 1 by 6. Therefore, this ni by n represents the probability that you will have ni number of particles in a particular ith state. Therefore, ni by n is the probability. Therefore, your average of anything, ensemble average of anything, you will be able to write as sum over I is equal to 1 to n pi xi. Xi, I told you earlier that xi is the instantaneous value of that given property. By using this equation, Gibbs was able to show that average of any property can be found by this equation. That is, average x is equal to, the only condition is that the n must be very large. The n, if n is very large, sum over I is equal to 1 to n pi xi. And the only thing that is needed to know is how to find this probability. To find the probability, Gibbs considered 3 different techniques. The first technique is if you are studying about a system, keep the energy, volume and number of particles constant and then study about the system. In another case, he took another case where he kept temperature, volume and number of particles constant and studied about the system. In another case, he took temperature, volume and chemical potential. Chemical potential is the work done to remove the particles, dW by dN. He kept temperature, volume and chemical potential constant, and then he found out the probability. These three methods are called as, the first method is called as the microcanonical ensemble, where energy, volume and number of particles are constant. The second one is temperature, volume and number of particles constant, and the third one is temperature, volume and chemical potential constant. You may be wondering why you have these three ensembles, why these three ensembles are necessary. That you will slowly understand what are the uses. These three ensembles have its own purposes. Microcanonical ensemble is the basic. It is actually connected with the development of the statistical mechanics, connected with Boltzmann's discovery of statistical mechanics. The second one is canonical ensemble, and the third one grand canonical ensemble. The best and the most useful one is grand canonical ensemble, that we will study later. First of all, and these three methods, these three techniques, it has its own advantage and also disadvantage. It's something like if you want to go to some place which is very nearby, you can use different types of vehicles you will be able to use. For example, if I want to move from A to B, position A to B, I can use either a cycle or a car or a bus or a lorry or some other vehicle. Somebody will say that I prefer cycle to travel. But if I want to travel from A to B, if A is in Kerala and B is in Australia, you will not be able to go to Australia by riding a cycle. Therefore, that is the way. Therefore, actually all these three ensembles also has got its own advantage. Some may be useful for deriving the basic thermodynamic properties very easily. Some will be very useful. Some will not be useful for that particular system. That is why we keep these three ensembles and then study about them. If you want to do some problems in which is a very complicated one, we usually avoid microcanonical ensemble, because compared to these three, sometimes it will be very, very difficult. But historically, the microcanonical ensemble has got great significance, because the basic ideas were formulated by Max Boltzmann in 1900. Therefore, we will be following the historical way of the development of statistical mechanics. Finally, you will also agree with this way of studying statistical mechanics: microcanonical ensemble, canonical ensemble and grand canonical ensemble. But as earlier I had said, I want to go from A to B. Finally, I will reach B. Whether I use any vehicle, I will reach B. Therefore, the results are the same. Whether you study in microcanonical ensemble, canonical ensemble or grand canonical ensemble, the final result that you get will be always the same. Okay, therefore, we will start with the microcanonical ensemble formalism, which was basically all the credit goes to Ludwig Boltzmann. Therefore, before studying this microcanonical ensemble, I will have a small idea about a small concept from thermodynamics. All your thermodynamic systems can be classified as extensive and intensive quantities. You have a large number of thermodynamic quantities like pressure, energy, entropy, susceptibility, volume, etc. For example, temperature. You are sitting inside a room, or I am standing in a room. If I put a curtain and then initially there is a volume for this room. If I put a curtain in the middle of the room and then find out what happens to its initial temperature, if the initial temperature is T, if I reduce the volume or if I change the volume of the room to two volumes, one is V by 2 and V by 2, your temperature will not change, volume will change, temperature will not change. Therefore, even if I change my volume, the temperature will not be changing. But what about energy? Energy, basically, if it is an ideal gas, energy will be given by 3 by 2 nKT. Temperature does not change, but the number of atoms and molecules inside each chamber will be halved. Therefore, energy will be changing. Therefore, those quantities, those physical quantities that does not depend upon the size or the volume, you can call it as an intensive parameter, and those depends on the size of the volume of the system, you will call it as an extensive parameter. Therefore, temperature is an intensive parameter, energy is an extensive parameter. Entropy, for example, entropy is equal to, by Clausius statement, change in entropy is equal to change in energy divided by temperature. Therefore, change in energy means energy is an extensive quantity, temperature is an intensive quantity, therefore, energy divided by temperature will again be an extensive quantity. Therefore, entropy is basically an extensive quantity. This you will be requiring greatly when you study microcanonical ensemble. All these things you might have studied in your undergraduate classes, but just I mentioned that only because you will be using this in your coming microcanonical ensemble classes. Okay. Therefore, we will start with the microcanonical ensemble. This is what I had said is only a basic introduction about statistical mechanics, and my aim is in the first module I will be teaching on microcanonical ensemble. Boltzmann before 1900, he put forward a very important idea that entropy, which is a macroscopic property. Macroscopic property means you look from the macroscopic world and you measure that any property, it is a macroscopic property. I told you that this macroscopic property basically depends upon the movement of the molecules, that is the micro world. Electrons, atoms, molecules, photons, etc., they live in the micro world. Therefore, any property associated with the micro world will be micro property. And that Boltzmann said that if I want macroscopy, for example, if I have any changes in my blood pressure, that blood pressure measurement I can measure by using a sphygmomanometer, which is a macroscopic instrument, but that is due to the microscopic movement of the blood, blood or something that is happening inside my body. Therefore, that microscopic changes in my body affects the macroscopic properties like blood pressure. Therefore, by pressure changes because of the microscopic. Similarly, the movement of the atoms and molecules inside a container, electrons, photons, etc., electrons inside the sun, photons inside the sun, the movement actually creates the properties, the macroscopic properties. Therefore, actually there must be, if I want to find out a macroscopic property, basically I know that it depends upon the microscopic properties of the system. And that idea was coined by Boltzmann. Nobody still now know how Boltzmann coined that idea. It is there. Boltzmann said that this is the equation, this is the idea that I am giving to you, I am giving to the world. Actually, that idea changed the whole face of the people living, or the whole face of the different style of living on the surface of the earth. Different types of science developed after this idea. Boltzmann said that the microscopic property, which he called it as a microstate, the possible number of microstates, will give you the macroscopic property entropy. Entropy is a macroscopic property. He said that this S will be a function of omega, or omega is a microstate associated with the particle, That is the number, actually is a number, it is a number. Boltzmann said that S is a function of omega. What is omega, I will explain to you later, but by some examples we will be able to understand what is omega shortly. Therefore, what Boltzmann said is, first of all, let us derive the equation what was suggested by Boltzmann. He said that S will be a function of omega. Omega is the number of states available for a system. For example, if I have an electron, naturally in statistical mechanics we consider electron in a magnetic field, or even without a magnetic field we will have electron will be having two states. One is the up state or the down state. up state with a particular energy and down state with another energy. Therefore, those are the two micro states or the two energy states available for a particle, up state and down state. Two states are available. Therefore, omega for an electron whose spin is equal to half will be equal to 2. What Boltzmann said is that this omega will decide the entropy of, for a single electron it will not decide, but anyhow this is the content of what Boltzmann said. This omega will decide what is entropy. And if you have 2 electrons, what will happen? If I have 2 electrons, what we will have is, I mentioned to you that I have one state which is up state for one electron, and there is another state for the same electron, up and down state. Therefore, these are the 2 states possible for the electron. But if I have 2 electrons and this omega for the first electron, omega 1, I can say 2. If I have 2 electrons, then what happens is that my first electron will be in the up state, second electron can be in the up state. My first electron can be in the up state, the second electron can be in the down state. My second electron can be in the down state, my first electron can be in the up state. My second electron can be in the down state and first electron can be in the down state and second electron can be in the down state. Therefore, there are 4 possibilities. Therefore, for 2 electrons there will be 4 states available, both in the up state, one in the up and second will in the down, one in the down state and the second will be in the up state, or both of them can be in the down state. If you take 3 electrons, you can see that there will be 8 possible ways. Therefore, omega 1 for the first electron is 2, omega 2 for the second electron is 2, and the omega 3 for the third electron is once again 2. Therefore, if I have a collection of 3 electrons, my omega will be equal to product of the omegas, omega 1, omega 2 and omega 3. Therefore, my total omega will be always product of omegas. It will be always product of individual omegas. Therefore, according to Boltzmann, S is a function of omega. S is a function of omega. S is a function of omega. Now, I told you that entropy is an extensive quantity. Therefore, if I have 2 electrons, for the first electron entropy will be S1 and for the second electron entropy will be S2. Therefore, the total entropy will be always equal to S1 plus S2. Therefore, entropy is an extensive quantity. Therefore, total entropy will be additive. S will be equal to S1 plus S2. But omega, which will be multiplicative, omega, that is the number of microstates for the 2 electrons, will be multiplicative, or omega will be equal to omega 1 into omega 2. Now, you have S is a function of omega. Therefore, I want a relationship between S and omega. The only mathematical way of representing the relationship between S and omega, one is on the left hand side you have additive quantity, on the right hand side you have multiplicative quantity, and the only way of representing this is by using the relationship. From mathematics, you have logarithm of A into B is equal to log A plus log B. Therefore, S is equal to, if you want to represent the relationship between omega and S, the only way is use the logarithmic dependence, or the Boltzmann relationship now changes to S is proportional to log omega. S is proportional to log omega. This was where Boltzmann stopped. He proposed that the entropy of a system, of a macroscopic property, entropy of system can be related to the number of microstates by the relation S proportional to log omega. Omega is a number and S is Joule per Kelvin. It was Max Planck who had good communication with the Boltzmann. When he was trying to explain the black body distribution law, he wanted to use some basic ideas of statistical mechanics. Therefore, he transformed this proportionality into an equation by introducing a constant in between log omega and s, and that constant is k, and which is called as Boltzmann's constant. Therefore, the equation now becomes s is equal to k log omega. K log omega, this is the famous equation for microcanonical ensemble, where this omega will be always a function of energy, volume and number of particles. Omega will be a function of, you fix energy, volume and number of particles and study about the system. If I want to study about the system, there are a large number of properties, thermodynamic properties will be there. Therefore, I will be just fixing some properties and then study about the system. Why I fix 3 quantities, you will later see that this it is necessary that if you want all the properties, you will have to fix three variables. You will have to fix 3 variables. Here we will be fixing energy, volume and number of particles and study about the system, and such this equation S is equal to k log omega, which bridges the micro world with the macro world, is called as the bridging equation in microcanonical ensemble. Therefore, if you can find omega for any system, you will get all the thermodynamics. You will find all the thermodynamics. We will work out some problems and then find out how you can find this, or we will find out what are the ways of finding this omega. I told you earlier that omega for an electron will be equal to 2. You can find out that using the equation also. If the spin is given to you, your omega will be equal to 2s plus 1, where spin for the electron is half. Therefore, 2 into half is 1 plus 1 is 2. If I have spin is equal to 1, for example, photon, if I want to find out how many possible microstates are there for a photon, 2 into 1 plus 1 will give you 3. Therefore, omega for a photon will be equal to 3. Omega for a photon will be equal to 3. And earlier I had mentioned to you that omega will be the product of individual omegas. Therefore, if I have n electrons are there, my total omega will be equal to 2 raised to n. My total omega will be equal to 2 raised to n. Therefore, you have in the case of a photon, my total omega will be equal to 3 raised to n. Therefore, let us do some problems. First of all, I told you that in the case of a microcanonical ensemble, I will be fixing energy, volume and number of particles. These are the questions that has been asked for the, I will be giving you the questions connected with the gate, JEST and UGC. The questions previously asked for JEST, UGC and gate. Therefore, in microcanonical ensemble, which are the thermodynamic quantities which are kept constant? A very simple question, energy, volume and number of particles. The second one is the total number of accessible states of n non-interacting particles of spin half is. How many accessible states are possible? This has been earlier worked out. Omega is given by 2s plus 1, s is half, therefore 2 into half plus 1, which is equal to 2. For n particles, it will be equal to 2 raised to n. Therefore, the choice is A, which is 2 raised to n. Yes, a system of n non-interacting particles and distinguishable one. Spin 1 is in the thermodynamic equilibrium. What is the entropy of the system? What is the entropy of the system? Earlier, we have only found out what is omega. Earlier we have found out what is omega. Now you are asked for spin 1 particle. Thus, for the spin 1 particle, you have omega will be given by 3. Your omega is given by omega is equal to 2s plus 1. S is 1. Therefore, omega will be equal to 3. Therefore, if you have n particles, your omega will be equal to 3 raised to n. Therefore, what is your entropy? Entropy is given by k log omega, and this omega is given by k log 3 raised to n, and logarithm of x raised to y is y log x. Therefore, it is equal to 3 n k log, this n comes here, therefore, n k log 3. n k log 3. S is n k log 3. Yes, this was the question. Your answer is n k log 3. n k log 3. Yes, next one. Two identical systems at the same temperature and each having initial entropy S are placed in thermal contact. if you have two chambers and if I remove the partition and then I am allowing them to, or you can have a thermal partition where you can exchange the energy or they are in thermal contact, then the entropy of the combined system will be equal to, if I have entropy is S1 and if the second one is S2. I told you that entropy is an extensive quantity, therefore, the total entropy will be equal to S1 plus S2. Therefore, the first one is S, the second one is S, the total entropy will be equal to 2S. The answer is D. Yes. Next is a very interesting one. You have entropy is given by n minus nk minus kn p log p plus 1 minus p log 1 minus p. Therefore, where p is the probability, the value of p at which the entropy is maximum, the value of p at which the entropy is maximum, I want to find out what is the value of p at which the entropy is a maximum. Therefore, I have entropy is given by minus nk in the bracket p log p plus 1 minus p log 1 minus p. This is your entropy. I want to find out when is this entropy a maximum. When is this entropy a maximum? For any function to be a maximum, you have a function some y is equal to x, and if it is a straight line, if y will be x will be y equal to x will be a straight line, or if I have a function like this, this is the point where this function, this is y and this is x, this is the point where y is a maximum, or this is the point where y is a minimum. Any point where you want to find out y maximum or minimum, what you have to do is take a simple differentiation and put that is equal, because there is no variation here. At this point you can have two values will be here, here two values will be there. At this point y will be having one and only one value. Therefore, at that point your differential will be equal to 0. Therefore, if I want to find out where this S will be a maximum, what I have to take is I want to take a derivative with respect to P. Therefore, when I take a derivative of this constant, that will be equal to 0. Therefore, I will find out what is the ds by dp and put that equal to 0. I will put that is equal to 0. Therefore, how will you differentiate this? I have p log p. Therefore, first of all, these are two variables are there. Therefore, p log p, I will first I will keep p constant, log p I will differentiate. Therefore, log p is 1 by p plus log p is there, I will differentiate to p. Therefore, p with respect to p, therefore dp, therefore that is gone, that is gone. Therefore, plus I have this 1 by 1 minus p log 1 minus p, differentiating I will be getting 1 by 1 minus p, and there will be a negatives minus p I am differentiating, I will get minus 1 plus log 1 minus p, and 1 minus p I have to differentiate, I will get a minus 1, I will get a minus 1. Therefore, this p by p is equal to plus 1 plus log p. This is 1 by p, 1 minus p, 1 minus p, minus 1. Therefore, this is minus 1 and I have minus log 1 minus p. Therefore, this plus 1 and minus 1 will go. I have this ds by dp is equal to 0, which will be giving me, that is 0 is equal to logarithm of p divided by 1 minus p. Logarithm of p is here minus logarithm of 1 minus p, that is now equal to 0. Therefore, logarithm of p divided by 1 minus p is equal to 0. From mathematics, you know that logarithm of 1 is 0. Therefore, p divided by 1 minus p is equal to 1, or p is equal to 1 minus p. Therefore, 2p is equal to 1, or p is equal to half. P is equal to half. Right. Now, I have been giving you a basic introduction on statistical mechanics, and statistical mechanics basically consists of three ensembles: microcanonical, canonical and grand canonical ensemble. I had just given a basic introduction on microcanonical ensemble and the basic equation S is equal to k log omega, and I have also given some problems for finding out how you can find omega and then to find entropy. These are the things that I had given you in this section. Okay, thank you.